Okay, so what I'm going to do today is continue my discussion of the theory of a weak gravitational wave propagating through flat space-time. Next week we will talk about gravitational waves propagating through the real lumpy universe with black holes and galaxies and so forth, and we will study effects like the gravitational lensing of gravitational waves, gravitational redshifts of gravitational waves, and the extreme smallness of dispersion or scattering of gravitational waves. So we'll get some feeling for how interaction with material in the real universe influences a gravitational wave. But for today, we're still in the simple situation of a very weak wave propagating through flat space-time. And we have in front of us two different mathematical descriptions of the gravitational wave that we got to at the end of the last lecture. One is in terms of the proper reference frame of some observer who watches the gravitational wave go by and watches its influence on the relative motion of free particles. And the other is in terms of the transverse traceless gauge, in which the metric perturbation is equal to the gravitational wave field, the TT gravitational wave field. And so I want now, as the first thing today, is to contrast those two different descriptions of the same thing. And so the same thing that I have in mind is that I have two free particles in space. They could be the proof masses in LISA, or they could be the test masses of LIGO if we were to take LIGO and put it up in interplanetary space so that it didn't have to hang by its wires. So I have these two free particles, and I want to talk about their relative motion from these two different points of view. The first point of view is the proper reference frame of one of the particles, or proof masses. Let me call that particle A. So that proper reference frame is a coordinate system that is built along the whirl line of particle A. And in that coordinate system, particle A is absolutely at rest. It's falling freely, but it is at rest in the coordinate system, moving along the time axis. So the whirl line of particle A is precisely the time axis of the coordinate system. The coordinates are t, x, y, and z. Particle B, let me make this be the x-axis, and this, I guess, is the minus y-axis. Particle B, I will, for simplicity, put on the x-axis, but out at some distance that before the gravitational wave arrives, the proper distance between the two particles is L. And the gravitational wave is weak, so the proper distance will continue to be very close to L as the waves pass. The second particle, particle B, then will move along a whirl line which is influenced by the gravitational wave. So it wiggles in this coordinate system, and as we have seen, the change in its position for particle B is HJK transverse traceless, the gravitational wave field, times the unperturbed position of particle B. And that reduces, in this case our particle B is on the x-axis, and the waves are propagating in the z direction. So the direction of propagation is the z-axis, which is not exhibited in the diagram. This reduces to a perturbation in the x-coordinate that is just equal to h plus times x. Is there a 1/2 in here? I think there's a 1/2 in here. Okay. And there is no perturbation in the y direction because the particle is on the x-axis. Is that right? And I'm going to assume, for simplicity, because I want to discuss a very simple case, a wave that has only the plus polarization. And so I'm going to set h cross equal to 0. So to have a very simple example. Okay. So this general formula for the perturbation in the position of particle B just becomes, in this case, the particle B is moved back and forth in this proper reference frame by a distance 1/2 h plus, which I remind you is a function of t minus z times the unperturbed x separation between the two particles, which was L. So that's one property of this proper reference frame of particle A. A second property is that the metric in this proper reference frame is equal to the flat space metric plus corrections that are of order the spatial distance from the origin of coordinates divided by the radius of curvature of space-time squared. Radius of curvature of space-time being something that you have read about in your reading. It is something that is given by the fact that in this proper reference frame, the Riemann curvature tensor, then the magnitude of the components is just 1 over r squared. So that's the definition of the radius of curvature of space-time. Now in this particular problem, the Riemann curvature is entirely due to the gravitational waves. And we know that the r, j, 0, k, 0 piece of the Riemann tensor is just equal to 1/2 h j k transverse traceless with 2 time derivatives on it. Factors of 1/2 I can never get straight. Well, I don't need that factor of 1/2 here necessarily because I only need it in order of magnitude. And so in magnitude, then, this is h plus with 2 time derivatives, and I've chosen to use units where the speed of light is equal to. We'll in this course use the notation lambda bar is the wavelength of the gravitational waves divided by 2 pi. Just like h bar, Planck's constant, h bar is h over 2 pi. So that's the magnitude of the space-time part of the Riemann curvature, but all the other components are obtained from this just by various algebraic relationships, and they all have this same magnitude. Yeah, question?
So what is the method for actually finding that magnitude? Are you contracting twice? Or?
For finding this magnitude?
Finding the magnitude of the Riemann.
Okay, so we know we have a gravitational wave field. And I defined the gravitation. I defined HJKTT in precisely this manner, that it's 1/2 the second time derivative. 1/2 the second time derivative of this guy is equal to the Riemann curvature tensors. That was my original definition of the gravitational wave field.
Okay, so maybe this is an absurd question, but let's say I have the Riemann curvature tensor. How do I find its magnitude?
It depends on the situation. You need to know what the tidal forces are that are pushing things back and forth, for example, in the equation of geodesic deviation. In this particular case, the tidal forces are all due to the gravitational wave. And in this particular case, we have this formula which basically defined the gravitational wave field in terms of Riemann.
But so there's no way just given Riemann to find Riemann's magnitude?
Yeah, you go to a local Lorentz frame and look, and Riemann has 20 non-zero components, and you look down them and find the biggest value in the local Lorentz frame of any of those components. That's the magnitude.
Would that be quotient in the planet?
In a local Lorentz frame, so I'm asking you to do this in a local Lorentz frame, okay? Riemann will have certain behaviors under Lorentz boosts, and the magnitude may change some, but in any given situation, you typically have some preferred reference frame. You have some observer you want to talk about things in terms of. So I'm talking about defining something that is in order of magnitude quantity. So you introduce the reference frame of some observer in whom you're interested, which in this case is one of these freely falling particles, and you ask yourself, what are the magnitudes of the components, which are that are measured physically by this observer, and those are the magnitudes in this observer's local Lorentz frame. And you just find out what is the biggest one, and that is what I mean by, if you wish, that's the definition of this radius of curvature of space-time.
It's not an absolute quantity.
So it's not. It's something that is defined in order of magnitude, only in order of magnitude.
It's not a scalar constructed from Riemann.
It's not a scalar constructed from Riemann. It is a characteristic magnitude of the tidal forces that would be felt by objects of interest to you in a physical situation. Okay. So that's my definition of what I mean by a radius of curvature of space-time. And when you do this sophisticated mathematics, and I will refer you to that and let you do it as an exercise when we talk about the reference frames of accelerated observers in several weeks. When you do that sophisticated mathematics, you find, in fact, this formula is true, and the 1 over r squared that appears here really is components of the Riemann tensor in the reference frame of your observer. So there's explicit formulas that you can write down for these additional terms. And those formulas look like components of Riemann times spatial distances away from the spatial origin. I'm sure you would feel much more comfortable if I went more slowly and I did all that mathematics first, but I really want to get to physics along the way and come back to doing that. But it's good for you to ask these questions, because if there's any fuzziness in your mind, we should stop and clarify it. I'm not going to clarify it by doing the mathematics now, but I promise you'll get a chance to do the mathematics later and see it. And what I want to do now in the lectures is really explain things in what I hope is a clear manner. Okay. So I strongly encourage questions like that. Are there any more? Okay. Okay, so in this situation, the quantity that appears there is basically components of the Riemann tensor, which have magnitudes of the gravitational wave field, H plus, divided by the characteristic reduced wavelength of the gravitational waves. These waves may have some broad spectrum of wavelengths. So in that case, I'm asking about, well, what is the characteristic, some sort of mean wavelength, some representative wavelength at which the waves are strong. So what that says then is that in this proper reference frame of particle A, the metric is the flat metric plus things that are of order the gravitational wave field H plus times spatial distance from the origin, and I'm interested actually in the separation between these two particles, and so that spatial distance is L divided by lambda bar squared. So that's the form of the metric. And so what this says is that if L is small compared to lambda bar, then the metric perturbation in this reference frame, let me call it H mu nu, which is of order H plus times L over lambda bar squared, it's small compared to H plus in this reference frame. And that's why this reference frame is really the kind of reference frame you want to use when talking about physical measurements. You have a metric that is as close to being a flat metric in the sense that the metric coefficients are the flat values as possible, as is allowed by the presence of the space-time curvature. And as close means that, in fact, so long as the system you're discussing, which has size L, is small compared to a reduced wavelength of the gravitational waves, then the metric perturbation is small compared to H plus. And so you don't really have to worry about the metric perturbation when thinking about physical measurements. If you are interested in asking about the energy of a photon, that's the time component of the photon's energy projected on an orthonormal basis of your observer. But this coordinate system is already an orthonormal basis to very high accuracy, even when the photon is over here. It's an accuracy up to H plus times this small number. And so you can just read off the energy of the photon as though you were in flat space. You can make talk about physical measurements over the size of this system just as though you were doing things in flat space. However, the tidal forces, due to this same Riemann curvature tensor, the tidal forces are wiggling this particle back and forth. And so from the point of view of the proper reference frame, we really think of these tidal forces as being like Newtonian tidal forces that raise the tides on the Earth. we think of them as physical forces in a reference frame that is as close to Lorentz as possible. Physical forces that are moving this particle back and forth relative to the origin. So that's one mathematical description of the gravitational waves. The second is TT gauge. And then begin in TT gauge by writing down the metric perturbation. The metric in TT gauge, the metric is G alpha beta is eta alpha beta plus H alpha beta transverse traceless. And that is what it is up through first order in H. There will be nonlinear effects in Einstein's equations, so there will be something of order H TT squared corrections. But if H is like 10 to the minus 21, and this is like 10 to the minus 42, and we're not going to see it in your lifetime or mine. Now, I have simply asserted that there is a coordinate system in which the metric takes that form. It's an exercise for you this weekend to prove that that's the case. It's not a very difficult proof mathematically. We basically, to prove that you can transform by gauge transformations, you can transform to by gauge transformations that basically ripple the coordinate system, you can transform to a set of coordinates where this is the case. Now, the proper reference frame is really only useful on scales small compared to lambda bar, because when you get out to a distance of order lambda bar, the metric perturbation is becoming of order h, and you can no longer ignore, when you talk about physical measurements, the influence of h on the formula for the energy of a photon, for example. So the proper reference frame is useful only on scales around the particle of interest that are small compared to the wavelengths of the gravitational waves divided by 2 pi. By contrast, TT gauge, as you will see, in TT gauge, this formula, as long as this is a weak wave propagating through an otherwise flat space-time, this formula is useful, it's valid, it's correct everywhere for such a wave. So there's a big advantage of TT gauge in that you can use it to cover the entire space-time if all you've got is this weak wave, whereas the proper reference frame you can only use in the vicinity of a particle or your detector over scales small compared to a reduced wavelength. In fact, you can show that if you want to look at these higher order corrections, these are really the leading terms in basically a power series expansion in distance from the origin. And the first correction is order L over lambda bar squared, and the next correction is probably L over lambda bar cubed. I'm not sure. I think it starts then going up in units of 1 power, not 2 powers. But it's just the first term in a power series expansion. Whereas down here, there's no power series expansion involved in distance. It's a power series expansion in the strength of the wave. So this is really what you need to use if you have, for example, a big detector, a detector that's big compared to a wavelength, and you want to analyze it. You've got to use TT gauge. You can't use the proper reference frame of one of the particles in the detector because this is only because these higher order corrections for a big detector just become so big that you can't use the technique of thinking of this proper reference frame in flat space language. On the other hand, when you do have a detector such as LIGO, where the size of the detector is small compared to a wavelength, there's a big advantage to the proper reference frame. And that is that you can use all of your non-relativistic intuition to think about it. And that's why we can get away when we're thinking about the design of detectors without applying any sophisticated relativity at all in the case of LIGO. because we can do the entire discussion in the proper reference frame of the detector. Let's go on with TT gauge and ask about the motion of those particles in the case of TT gauge, where again I have the same wave, it's propagating in the z direction. I have two particles, one that's sitting at least initially on the at the spatial origin, and the other that is sitting at least initially out here a distance L away. And they both, before the wave arrives, they both are moving along in the time direction. They're at rest with respect to each other, at rest with respect to the TT coordinate system. Then the wave arrives, propagating in the z direction, which I have not depicted in this diagram. It passes through, and we want to know, what do the particles do? So particle motion, free particle motion in that case, it is an exercise for you to work out what the answer is. We've given an initial position and initial velocity to each of these particles before the wave arrives, and then you have to integrate the geodesic equation to find out how the particles move. So that yields the motion. And the bottom line answer that you're going to discover is that the particles have spatial positions that do not change in TT gauge, in this coordinate system. They don't wiggle at all. And so particle A just moves up the time axis. Particle B just moves up parallel to the time axis in the coordinate system. Its coordinate separation for particle A remains L. We can ask, how are these two pictures compatible? We can ask, how are these two pictures compatible? And the answer is, if you ask yourself, what is the proper distance between these two particles at any given moment of time, the proper distances are going to be the same. So let's just ask that. What is the proper distance squared between the two particles? Because they, in both cases, the particles are separated just along the x direction. At a particular moment of time, the separations are given just by gxx times the separation in the x coordinate squared. So in the proper reference frame, or the local Lorentz frame of A, gxx is equal to 1 plus hxx transverse traceless, or that's 1 plus h plus. I'm sorry, that's not the proper reference frame. Let me start over. In the local Lorentz frame of A, gxx is just equal to a to xx. Okay. Because these higher order corrections are negligible, I'm considering the case where the separation is small compared to lambda var. So gxx is just equal to a to xx, which is just equal to plus 1. And so delta s squared is just equal to delta x squared. But delta x squared is just, well, it's what I call little delta x up here. It's just equal to 1/2 h plus times L squared, or delta s is just equal to, let me back up. Let me start over again. Delta x, the separation, is equal to L plus 1/2 h plus times L. That's squared. Okay, because the original separation was L, and this delta x is a change in the separation. Okay. This little delta x. So this little delta x is that guy. It's the change in the separation. So delta S squared is L plus, to first order in H, it's L plus H plus times L, or it's L times 1 plus H plus. Taking the square root, delta S squared, delta S is equal to L times 1 plus 1/2 H plus. And to put my mathematics of ignoring quadratic terms in context, you want to remember that H is of order 10 to the minus 21, so H squared is of order 10 to the minus 42, and we can ignore it. It's a small number. So that's in the local Lorentz frame of A. In TT gauge, the separation between the two particles is delta S squared is GXX times the coordinate separation. Now GXX is equal to 1 plus HXX transverse traceless. And the coordinate separation is just L squared because the particles have remained at rest. So in the local Lorentz frame, the metric was unperturbed, but the particles moved. And so the delta X squared was the thing that was wiggling, but the metric was unperturbed. In TT gauge, the metric wiggles, but the particles remain at rest in the coordinate system. But since HXX transverse tracelet is just H plus, this is 1 plus H plus L squared, which is the same formula as I had up here if I had done it right and kept my L squareds. Or again, the same formula, delta S is equal to L times 1 plus 1/2 H plus. So the bottom line is the same. The proper separation, the physical separation that you would measure with a physical rod and clock between the two particles, it wiggles. In TT gauge, it wiggles by virtue of the fact that the metric is wiggling, but the particle is remaining fixed in the coordinate system. In the proper reference frame, it wiggles by virtue of the fact that the particle wiggles in the coordinate system, but the metric remains very close to the flat space metric. Now let's extend this discussion to discuss an actual physical measurement of the motion. In the manner that is done in LIGO. So let's suppose that we have one of the particles is here, the other particle is there, and it carries a mirror. And so light goes out from this particle, bounces off the mirror, and comes back. And we ask about the phase shift, the shift in phase of the light as a result of the influence of the gravitational wave. That's what LIGO normally measures. But we can also ask, if you wish, about the time derivative of the phase shift. And so that's a shift in the angular frequency of the light that you would measure. Okay, so you can ask about either one. If you compute one, you can, by a time derivative or an integral, you can get out the other one. And so in the proper reference frame, when discussing this, of course, you have to be concerned now not only about what the mirror and this particle are doing, how they're moving, but you also have to be concerned about the propagation of the light, which you could compute using Maxwell's equations, or you can compute by knowing that a photon should travel along a null geodesic through space-time. And so you have to worry about both. The influence of the gravitational wave. In fact, I want to make a little table here. Okay, so I want to worry about the influence of the wave on the light and the influence on the particles. And if you go through a detailed analysis of this, which we will do later in a few weeks when we start talking about the interaction, in detail about the interaction of gravitational waves with detectors, when we go through it in detail, we will find the following, which should be fairly obvious already from the things that I have said. In the case of the local Lorentz frame of the particle that emits the light, that goes out and bounces off and comes back, if we discuss the influence of the wave on the light, well, that has to do with the geodesic motion in a metric that is, for all practical purposes, flat. And so there is no influence in terms of components in this coordinate system. The components of the formal momentum of the photon in the coordinate system remain conserved. In Maxwell's equations, the metric perturbation just won't enter in any significant way in Maxwell's equations if you do this by solving Maxwell's equations. So in the local Lorentz frame, there is no significant influence of the wave on the light. However, on the particles, there is an influence. They move by the usual delta x is equal to 1/2 h plus times L. So the particles move. You get that motion by solving the equation of geodesic deviation, which is basically what underlies this entire discussion in proper reference frames. But the light is unaffected. In TT gauge, there is no particle motion relative to the coordinate system. But if you solve Maxwell's equations at first order in H, there will be an influence on the form of Maxwell's equations. If you solve the problem by looking at the geodesic motion of a photon, at first order in H, there will be an influence on the geodesic motion on the frequencies of the photons at first order in H, and correspondingly on the frequency of the returning light at first order in H, correspondingly by doing one time integral on the phase shift at first order in H. So in the case of TT gauge, there is a delta phi that comes, influence on phase shift, that comes about through the interaction of the wave with the light, delta phi that is of order h. And so, very different pictures of what's going on. And then to reiterate, as long as your detector is small compared to a wavelength, the local Lorentz frame point of view is really the preferred one, so far as I'm concerned at least, because I can think about everything in the way I would in flat space-time, and I don't have to carry around the baggage of general relativity to think about it. And that's the case for LIGO. For LIGO, we have arm lengths of 4 kilometers. We have reduced wavelengths that are a characteristic period of the gravitational wave, which is about 1/100th of a second, divided by 2 pi and multiplied by the speed of light, which is 3 times 10 to the 5th kilometers per second. And so 3 divided by pi is about 1, and this 1/2 gives me an 0.5. So this is 0.5 times 10 to the 5th and times 0.01 is 10 to the 3rd, or it is about 500 kilometers. The reduced wavelength is about 500 kilometers, the arm length is 4 kilometers, and so you are in the regime with LIGO where you can get away with working in the proper reference frame of the observer, at least until LIGO starts making measurements at levels of accuracy that are 4 divided by 500 squared. So when LIGO gets down to measuring with accuracies of 10 to the minus at 100 hertz, accuracies of a part in 10 to the 4, then you've got to worry about a more accurate description of the detectors than we normally use. But for LISA, the wavelengths are typically comparable to and sometimes longer than the arm length separation, and you're forced into using the TT description. Okay. No.
Is the fact that you sort of have this increased wavelength into the referral cavity enter into this calculation at all?
So the question is,
increased arm length.
yeah, so you have in effect an increased arm length because you store the light in the cavity. In fact, you store the light in the cavity for about 100th of a second, and so the effective arm length is increased to of order, it's from 4 kilometers to of order 500 kilometers. Okay. And the answer is no. From the mathematics, it should be clear that your analysis will still work, and that the issues that arise from storing the light for such a long period of time, or even longer, are issues that can be analyzed entirely using techniques that ignore general relativity. So they're issues in optics, and they're issues that we will look at. So the detector does behave rather differently when you're storing the light in the detector for a time that is long compared to a gravity wave period than when you store it for a time that's short. But different for reasons of optics that you can analyze without knowing any general relativity if you work in the proper reference frame of the observer. If you work in the TT gauge, you've got to think about the relativity sort of all the way through. Okay. Yeah.
Okay, so is there a reason we can't work in the local Lorentz frame and use the higher order correction?
You can, except that the series won't converge when L is of order lambda bar. And so you can use them when L over lambda bar is of order a tenth or maybe a third, yeah, you can do it. When L over lambda bar becomes of order unity or larger, the series won't even converge and you just get nonsense. Yeah.
LIGO stores light for what, like a millisecond, which is long which is comparable to the times that it takes away to get through it.
So in the first interferometers store light for of order a millisecond, that's right, which is of order the time it takes for the wave to get through. And so there are issues of storage time being comparable to a period of the wave. And so the analysis of the details is not entirely trivial. It's not just as simple as if I had bounced the light back and forth once. But those issues are all issues in standard optics, where general relativity is not going to play any role because they're issues in optics using a metric where the metric perturbation is throughout the detector small compared to H plus. And so you don't need to, you can separate out the general relativity issues and ignore them. You can discuss LIGO entirely without knowing any general relativity except for the fact that the gravitational wave pushes the arms back and forth, as long as you do it in the proper reference frame of the observer. Not true for LISA because of the long arm length. Okay, other questions? Yeah.
Are you going to talk about pulsar timing?
So am I going to talk about pulsar timing? No, not today. But let me talk about it to this degree. So when you have a separation that is where the separation is comparable to or longer than a wavelength, then you can't use the proper reference frame of the observer. You can use TT gauge. But in TT gauge, you have this factor of H coming in and influencing not only the light propagation, but also ticking rates of clocks. And in fact, pulsar timing is a technique for searching for gravity waves, works on the basis of the influence of the wave on ticking waves, of the gravitational wave on the ticking rates of clocks. In pulsar timing, it's made particularly simple because any wave we're talking about is going to be, because the distance between the pulsar and the Earth is so big compared to the wavelength of the waves that it's unlikely that that the waves that are sweeping over the Earth are at the same time in any kind of a coherent manner sweeping also over the pulsar. And that is, you can basically regard the pulsar as being outside the gravitational wave train. Particularly in an experiment where what you do is you compare the timing rates for this pulsar, that pulsar in the sky, a bunch of different pulsars. There will be correlations between the fluctuations in timing of all these pulsars as a result of a gravitational wave sweeping over the Earth and influencing the ticking rates of the clocks on Earth as described in TT gauge. But over those huge distances between the pulsars, there should not be any correlation between what the wave is doing as it passes this pulsar versus what it's doing when it passes that pulsar. And so it's a very good approximation in discussing pulsar timing to just assume that the wave sweeps over the Earth and that it's not even in the vicinity of the pulsars, and then discuss the correlations in the timing fluctuations of different pulsars at different locations on the sky. And that can all be done using TT gauge because the waves, TT gauge is a coordinate system in which you can cover the entire space-time with these coordinates, so long as we're not concerned about the gravitational influences of the galaxy or other objects that the waves go by. So that's sort of in words the story, and later in the term when I discuss in more detail interaction of the waves with detectors, we'll look at that quantitatively and I'll assign a problem on that. Okay, other questions? Okay, so let me move on then. So I'm done with it. Anything you're interested in, you can leave out. Let's see. So I now want to do a very first cut at gravitational wave generation. We'll return to gravitational wave generation in detail after we discuss detection in the mathematical theory of detection in some detail, after we discuss propagation through the real curved lumpy universe. But I want to do a first cut at it, so just to have it in front of us at this early stage in the course, so I can refer back to it from time to time as we discuss other issues. And so I'm interested in applying the Einstein field equations to compute the gravitational waves that are produced by some source in the universe. And to make this tractable for a very first pass, I'm going to assume that we have a source that has very weak internal gravity, to the point that I'm going to even ignore its internal gravity, so all its motions are produced by internal stresses. That's not true of astrophysical sources, and I'll comment on what's different in the case of astrophysical sources, where it's the self-gravity of the system, such as a binary star system, that is generating the motions that then in turn produce the gravitational waves. But for a very first pass at gravitational wave generation, I want to make it as simple as possible, so I'm going to ignore the internal gravity. So that, for example, what this source might be is two masses on the end of a rod between them that are rotating and emitting gravitational waves. And as they rotate, there are internal stresses in this rod, of course, that keep the masses from just flying apart. So that's the kind of a source I want to talk about. We have such a gravitational wave source over in Taper in the interaction room. It was built by Jekta Gersel at the time he was a graduate student in our group. And I think it was probably given to Ron Drever as a gift, and he gave it to us to leave in the interaction room. And at some point, I'll invite you to calculate the rate of emission of gravitons by that gravitational wave source. But for the moment, we'll delay that until a little bit later. Okay, so this is the kind of a source I want to discuss. And I'm going to discuss it by looking then at the Einstein field equations, which say that the Einstein tensor is 8 pi times Newton's gravitational constant times the stress energy tensor. And I presume now that although I have not discussed in any detail the concept of the stress energy tensor in this course, I presume you have read about it, and by now you feel comfortable about it. I've assigned problems on it for those of you who are not familiar with it. And if anybody has any difficulty with this concept, come around and talk to me or to the TAs, or particularly come to the discussion session that I will do next week. Next week I'm going to have to probably do the discussion session on Tuesday rather than Monday because of a faculty meeting I have to go to. But I'm happy to discuss it. Send me an email and I'll set up an appointment to talk to you or talk to the TA